last class we discussed about the importance of relations in order to solve problems such as what we describe here, delta u. Okay, and in order to get this expression, we need to convert such an expression in something measurable quantities. Okay, and that is what we are going to discuss today, and this is something which we can make use of Maxwell's relation. Okay. So, I will just quickly describe this and then we will try to get back to this particular expression. So, let me just take a function f, okay, and what we are interested is so this we can write it this as del f del y del x, okay, or you can also write this as so the point is that order of differentiation is unimportant. Okay. So, we can make use of this this expression in our thermodynamic relation. So, I will just take a case of u. U is a function of SVN. So, f is basically u, and let us say x and y are v and s and v, right. So, f is nothing but u and x is let us say you have s and v. Okay. So, we are just dropping n here, considering this to be a pure case. So, this is going to be, I can write it in this way. Okay. So, let me make use of this expression here, this one. Okay. Now, what is this? Minus p, and this is going to be t. So, essentially what you got is del p by del s at v is equal to del v by del t at s. Okay. So, this is one thermodynamic relation or Maxwell relation we call it. Okay. Now, this we can generalize it also. So, you see the way I did was I made use of this this order of differentiation. Okay. Now, you need not do this in this way. You can simply make use of the fundamental equation in differential form for different thermodynamic functions and directly use a basic general properties such as what I am going to write here. If phi is a function which can be written as x2 dy 2 plus x3 dy 3 and so forth, then del xi by del yi for a given y k is same as del xj by del yi for the same yk. That is what it is trying to say. Okay. Now, you can relook at from this perspective that I am going to write this different fundamental equation del u is equal to t ds minus p dv, okay, plus mu dn. Okay. So, mu I let us say di. So, now for this you can clearly get the expression because that is what I talked about is del xi del y I this form. Okay. So, you have del xi del y. So, this is nothing but equivalently you can say this is nothing but del t by del v, okay, del t by del v yj. Okay. So, this would be same as minus of del P by del S. Now what will be constant here? So for this one, this will be S and all ani's, right? And this is going to be your V and all ani's. Okay. So many times I may be writing just like Ni, it means basically all, or I can use the curly bracket to say that is all the ani's of. Now we can easily write for others quickly without too much of thinking. Okay, so I'm going to write this as del V by del S P and I constant V. No, this has to be del V by del S and del T by del P at constant S. Okay. Now you can also use inversion. You can make it this as to be del P by del T. Okay, that will be equivalent to del S by del V. Right. So this will be using expression using inversion rules. So here we get more important terms. Here we get del S by del V T and I is equal to del P by del T V and I, and here we get minus del S by del P T I. Okay, so these two terms, which is quite important. If you look into the last two Maxwell relation, this relates the entropy to the PVT data, and PVT data you can extract from the experiment. Okay. So this is why it becomes a very important expressions for us. So in addition, we are going to also write down the other variables which we are often going to use, that is the definition of Cp, okay, and Cv, okay. Now let's go back to the expression of del U. So what we needed? We needed to get this and this. So this is nothing but, this whole thing is Cv, right? What about this del S by del V? Let's look at del S by del V expressions. So del S by del V is nothing but is del P by dou P by dou T or del P by del T. So we can directly now write down the expression. Okay, so what we have now, final expression is delta U in terms of measurable variables. Okay, so we had some value V2. So this is one path. Okay, the expression will be slightly different. Okay, the only thing is the constants are going to be different. Okay, if we use another path. So this whole thing will be at constant T is equal to T1. Okay, this is one path which I have considered. So one way I have considered V constant taken to temperature T, and then the other one is we consider T constant. Okay. So remember that what we are interested is to make all this exercise is to make use of measurable quantities such as Cv, Cp, and we are going to define compressibility, expansion coefficient, delta H changes in enthalpy, because you can use calorimetry and all this thing to get a delta H. Then you can also use this equilibrium constant. This is also easy to find. equilibrium constant of reaction, EMF of cells, okay, vapor pressure, solubility. These are all, this you can find out from experiment, okay. These are measurable quantities, okay. So, we have to make use of our thermodynamic variable changes in terms of these quantities, okay. So, let me try to comment here, because we talked about compressibility and expansibility. So, kT is minus 1 by V, dou V by dou P, constant temperature, and of course, you have all other thing constant, and then alpha is 1 by V, del V by del T at constant P, okay. Now, these are positive values, okay. These are positive values, and we can show that later also, that what del V by del P should be negative for stability and so forth, and hence K should be positive. Okay. Now, remember this also, that this compressibility, inverse of the compressibility or reciprocal of K sometimes is also called bulk modulus of the material. You can show that similar to the way we have done this expansion coefficient. You can show that the pressure coefficient, so expansion is volume is basically expanding. So, pressure coefficient, which will be 1 by P del P by del T at constant V, can be shown that this is nothing but alpha by P K T, okay. So, you can show that, you can also prove that, okay. So, this it is also useful to see how the pressure is changing as you change the temperature for a constant volume, okay. You can also prove or show that the Cp minus Cv is Tv alpha square by K, okay, and for ideal gas you can show this is nothing but R, okay. Other expression which you can derive is something called isentropic compressibility fractional change in volume of a system undergoing a reversible adiabatic compression. And you can show that this is nothing but minus 1 by V. Basically, the expression here is minus 1 by V del V by del P, because you are compressing it, entropy constant, adiabatic compression, entropy constant, reversible adiabatic means entropy constant. And this expression you can show this is nothing but Cv by Cp multiplied by K. So, you can prove that. So, all these things you can connect to the measurable quantities, whatever you desire to do that, okay. So, the way we have done or derived for delta U, in a similar way you can actually also calculate the expression of delta H, okay, going from P1 T1 to P2 T2, and similarly for delta S in a measurable quantities, okay. So, I will just try to put down the equation, okay. So, for example, in the case of delta H, S2 minus H1, you can show that this is nothing but T1 T2 Cp dt plus P1 P2 V1 minus alpha T dP, okay. I mean, it is very easy to actually derive, you can always do a path based calculation, because you can start from ds is equal to, or dH is equal to Tds plus Vdv, and from here you can do the next few steps to get to this expression, okay. Okay, so I think as far as the Maxwell relation is, the derivatives are concerned and usage are concerned, I will stop here, okay, and just in the next lecture we will talk about quickly on the stability aspect of it. you.